people looking for jobs up there? Alright, so my name is Andrew Bothwell. I'm representing the risk and reliability team. This is going to be a fun few minutes here. I guess we'll start off, I worked on this team with Christina Gonzalez, and I guess we'll start off with risk first. So, we basically address risk on two primary scales, criticality and probability. Criticality was mainly defined by the impact that a certain component or assembly or system would have on a mission schedule or its necessity to accomplish a mission. Probability, on the other hand, was mainly concerned with the complexity of a system or component and its readiness level for space flight. These criteria were rated from 1 for low, 5 to high. They were taken from a systems engineering textbook. Next slide, please. Hopping right into the vehicles here, we'll start with the orbiter vehicle, with the ASRG first. We've had a few of these issues actually addressed already throughout our presentation, as well as many other risks that we now need to address further on. The ASRG is a new technology, and in the orbiter we try to mitigate its risk by working through due diligence and hard work to make them redundant. We can stand to lose one ASRG on the orbiter vehicle, so therefore we don't count it as a single point failure. Also, the main thrusters are an issue. The main thruster is an issue. We, as stated earlier by the propulsion team, we need that main thruster to operate successfully through the second Earth flyby, which is about 4 years into the mission, in order to accomplish full scientific RFP requirements. However, if we lose it beyond the second Earth flyby, we can still accomplish everything minus the moon and ring tour with the backup 200 thrusters. Also, tank development was listed there as more of a watch item. Obviously, you brought up a good point with maybe standardizing a single tank design that can apply to both fuel and ox. But it is, as you all know, it's not a very new technology. It's just something we need to watch out for to make sure development catches up with integration and finally launch. The launch window of the orbiter spacecraft is of concern primarily because we only have one launch window. We try to mitigate that by making it a longer launch window. Originally it was only a couple weeks long through due diligence on the orbit team. We were able to increase that to over a month. So that is how we address that issue. Probe separation is an issue that will come up with each of the vehicles. Basically, the detachment separation mechanisms are electrically redundant. There are no electric single point failures. However, there is a mechanical single point failure with the spring mechanism that is used to separate them. Also, the high gain antenna is of concern to us. It's there's only one, and if we lose it, we can't transmit data back to Earth. However, it is I don't want to say simple design, but it is customized for our design, and but we're testing it as a structure, and we're hoping to go through proper channels there. Any questions before we move on?
Yeah, let me focus the launch window.
Yeah.
So, if I understand what you said, it sounded like you guys increased the launch window. Is that the only thing that went into that?
I mean, unless...
Did you guys look at the schedule, what the critical path is, and those type of things as far as...
I mean, unless Orbitz wants to comment on that, that was my understanding was the fact that we have one launch window.
Yeah. So you've only got one launch window, so if you lose that, how much of your mission do you not satisfy?
Well, the orbiter spacecraft is extremely crucial to our mission. It provides easily 90% or more of our mission requirements, so it's imperative that we get that off the ground during its scheduled launch window.
So that's why the criticality is 5 then.
Exactly.
So that criticality is never going to go below 5.
Yeah.
My problem is it's not red. We're just talking here that somehow that one ought to be red.
Attribute that to a typo.
That's the nature of
I know. It just doesn't feel right.
Yeah, and I agree with. So what we end up doing when something happens like that, we say that's nice. We're calling it red anyway. We're treating it like it's red. And hell with what the tool says.
Yeah.
So I totally agree with you.
And I'm in agreement with you. I'm not going to disagree. Let's put that.
One last quick question on this one is that it's kind of showed on your list here, is most of the items are bus or launch related. And you show instruments at the bottom, but you're only showing 2 instruments. Are those the 2 major instruments that are above them? Or
Oh, yeah, sorry, I didn't do this earlier. So each of the instruments are, if we lose one of them, the data that you would lose from it could be somewhat accommodated or replaced by data from another instrument, except for the magnetometer and the rolling. I guess each of those provide specific data that the others simply cannot replace. So yeah, I should have.
But the instruments are interesting.
Yeah?
Because on the one hand, I mean, they hurt the mission. On the other hand, unless they fail because of something the vehicle does to it, they're CFE. That's his problem.
No, it doesn't.
So push them off on the customer. It is bad. So I mean, you know, Dave doesn't give you many opportunities to stick it back to him.
Especially when I have industry professionals backing me up.
There's an action to take that off the list.
What?
You just gave them an action to take that off the list.
Now, in the mid-system point of view, from the customer's point of view, that's a risk.
Okay.
Right. As is the launch vehicle.
I mean, what would you do as mitigation against the failure of magnetometer? Or there's not much you can do, they're not in your control. You're not budget authority or schedule authority, or you can't do anything about it.
Okay.
Sometimes it doesn't hurt.
We should address that.
Let's not forget the customer often needs help.
Customer
We
may
have to
not
watch
always
out for them a little bit.
Yeah.
And did I hear you say that 90% of your mission is accomplished with the orbiter vehicle?
Yeah, those instruments that are on the orbiter vehicle, they provide almost all of the total scientific data that our mission is meant to achieve.
So is that the answer, that 90% of your mission is done with the orbiter vehicle?
Yeah, in
That's
excess.
just given us an excellent cost-cutting device.
Yeah.
Yeah.
So let's look at
And then all that money, you say double up on these, and then you extend both booms on day 1 for your balance now.
Well, we're taking another look at that number.
Are there any more questions on the orbital vehicle? Yeah. Next slide, please. All right, as mentioned earlier by the structures team, the payload attached fitting was of concern to us with the UPS vehicle. Although, as they mentioned, basically the way we're dealing with that is we're going to do some low-level analysis with the payload attached fitting and then develop a set of developmental design requirements, which we then send to the launch vehicle provider, and they would design it for us. And also, the ASRG presents a different...
That doesn't let you off the hook.
Yeah.
You guys still own it.
So,
because
yeah.
you're subcontracting.
But why is the probability so high? I mean, that's not rocket science.
I guess not. I think the reason why we
Even though the rocket science.
But hire Rulag in Sweden, I'll do it for you.
Okay. I think the reason is just because it hasn't been made, and I guess you're right. It's
I mean, it's not like you're launching 2 years from now. You're launching, what, 8 years from now or something? So there's plenty of time to develop.
And it's not like plug-in systems for multiple satellites on a single launch vehicle have been done before.
okay.
That's been done successfully.
So, right. The ASRG presents a different kind of problem with the UPS vehicle because there is only one ASRG on the vehicle. Therefore, if we lose it, that is technically a single point failure for the vehicle. We will have no way of providing power. And so far, the only way we can really mitigate it is try to provide the ASRG with as optimal of a home as we can during the course of its mission. Also, it's important to know that, I guess mentioned earlier, ASRGs are rated, I guess, expected to be rated for around 14, 15 years. That is the average life expectancy of one UPS vehicles. So that's kind of how we're addressing it currently. Similar situations with the tank development and probe separation. The launch window is a little different. As you guys heard before, there are 2 launch windows, so we do have a backup in this case. Although, again, as you guys mentioned, that may not be.
I thought the tank was 8 existing?
For the UPS vehicles, are we using a existing tank?
For the pressure tank?
The pressure intake is custom made, but the actual hydrogen tank is off the shelf.
Yeah, okay. That's what I was wondering.
But even then, it shouldn't normally be that critical. Well, it's critical.
But don't you have a fallback for the ASRG? Can't you do this with MMRPGs?
Well, that's a good question. I think Power may have considered that. The question was, have we done any research today looking into using a backup power system in case the ASRGs just don't work for them?
We have looked into using the MMRTGs. Their power output is a little lower than the ASRGs. In addition to that, the surface temperature of the MMRTGs are considerably hotter than the ASRGs, so that does present some integration issues. Yeah, those were the issues that we've dealt with. That's why we wanted the ASRGs for the reasons that I mentioned.
Yeah, we're talking about risks. Let's say the ASRGs fall off the table and you can't get them.
Okay,
You save your mission by going to our MMRPG.
Oh, well, there are going to be pretty heavy modifications, more than likely, to the orbiter and the UPS, just because of the different characteristics of the MMRTG, such as the hotter surface temperature that I mentioned. It's potentially we can't just mount them in the same way that we're mounting the ASRGs. We may not even be able to keep them in close proximity like we do the ASRGs. More analysis needs to be done into that, but that is what we came up with when going with the ASRGs, rather than
I'm still agreeing with your choice for ASRGs.
Yeah.
But I'm saying it's not that hard to put one in if there's no other way to do the mission. So that's the risk mitigation policy.
Yep.
All right.
Anything else? I guess if there were questions with the UPS, we can move on to the probe. All right, next slide. So the probe, again, similar problems with separation mechanism failure. I mean, it's just kind of the opposite side of the coin, UPS or orbiter. Also, there's an issue with the timer mechanism that we are using. Once the probe is detached, timer mechanism is supposed to count down, and once it gets to a certain time, it will turn on all the systems within the probe. There is no redundant timer, so if that timer doesn't work as intended, then the operations will not happen when we want them to. However, we plan to mitigate that by activating a G switch, which will basically use the accelerative loads to activate the probe to turn on, essentially. The problem with that is you'd basically start taking data at a lower altitude than you originally intend, so that would result in a decrease or a degradation in the probe mission.
How much of a degradation would you estimate it would be?
I think the probe team may be able to handle that question.
Could you please repeat the question?
Oh, the question was, if the timer should fail and we can't start taking data with the probe until the G switch is activated, around how much data do you think we could expect to lose?
The G switch would flip at 5 Gs, which would mean that our system would be turning on just after probably about 30 seconds in. We haven't done the analysis on how much we would lose, but we would be able to collect the bulk of data, and we would certainly be ready to go when all of our main instruments turn on to full load.
Does that answer your question?
So there's some minor degradation.
Yeah, you would get some data. Also with the probes, with the various deployables, the rear heat shield, drogue parachute, main parachute, if failure were to occur on those mechanisms, it wouldn't result in total mission loss of the probe. It would, there are backup measures which would, just because the drogue doesn't deploy, the rear heat shield still has the ability to deploy on its own. Understand that correctly? Therefore, again, you would just have decreased data degradation. The only real single point failure that we can identify was the front heat shield. If the ablative, for instance, were to wear off during re-entry, during entry, then you would essentially lose the probe. You may get some accelerometer data, but that's it. nothing really beyond that. The insertion accuracy was kind of a concern with us too, but like I said, that problem is mitigated by the sensitivity analysis done by Orbit's ADCS. So I guess there's no more questions on the probe. Yes?
We didn't hear anything about the parachute, and we don't understand. I don't know anything about parachutes, but is the design within the operation or the parameters that are normally done for Mars shoots or whatever other shoots that are out there?
Yeah, actually our parachute guy is here now. So,
is the parachute design very conservative, or is it?
It's, I'm not an expert on parachutes, it was difficult finding good information on parachutes, but we did have a book, and with the parachutes we chose, we should be within the parachute deployment boxes for what we're expecting in atmosphere. Also, we plan to do wind tunnel testing and a drop test, so that will really verify if the parachutes are going to deploy properly for the dynamic conditions.
Did you use like Viking parachute data or something? You know?
Yeah, we're looking at other probe parachute data. We are using a Viscat band parachute, which is really common for many probes. For our drogue parachute, the guided surface, which hasn't been used for a probe before, but is commonly used for supersonic missiles on Earth.
Yes, sir.
There's a question. So I have two probes. They're all collecting identical data.
Yep. Well, just at different times.
That's fine, but
the same.
Would you say that I've got 3 ways to collect the data, 2 of those are redundant from a mission perspective?
We would, however, the RFP was clear in saying they wanted 3 probes dropped. So, yeah.
So that's somehow you're rationalizing that you don't have a single point failure with degraded mission data.
Yeah. So that's how we're viewing it. I mean, if that's an incorrect assumption, certainly revisit how we find it.
Maybe you can negotiate with the customer.
So from a discussion of risk, I'm used to having stuff on a risk chart that I can do something about.
Yeah.
Tank development, for example. If I have trouble developing tanks, I can have a parallel tank development, or I can, do something about that as I go through the development cycle. Main parachute failure is something that I need to design against from 0 to certain point failure or something like that. It's not something I can do anything about once the mission is started.
Yeah.
Okay, I can do something about it from a design point of view to begin with, but I can't, once the mission started, you roll the dice, that's just the way it is. So, I'm used to thinking about risk as something I can do about an instigated mitigation plan during the development of the mission, not just worry stones about heat shield failure.
Isn't there a program risk chart somewhere? Anybody where you're going to put you guys well? Like the risk of not, like the ASRG, if it wasn't qualified,
Yeah, ASRG development, getting stuff in, and I guess kind of the case too is that that's kind of what we kind of lumped in the program risk, but we kind of pushed it out with the vehicles too.
What the gentleman was just saying about overall program risk is a lot more than that.
The front heat shield failure is one thing. It would be during development, I do testing and I have a failure of my heat shields. I'm going through development testing and I have to have some sort of backup against that. But just general front heat shield failure of the mission is not what you're worried about. What you're worried about is that when you launch it, the front heat shield will have passed all of its qualification testing and you believe it's going to work when it gets there. Okay, to me there's a difference.
So, put it another way, but we'll do stuff like this, but there's another piece to this. And that is, for each one of those bullets that you've got up there, there's a risk mitigation plan that says, here are the things we're going to do to mitigate the risk. Here are the dates we're going to have to identify. Here's who's responsible. Here are the exit points. Here are the alternatives.
Risk mitigation plan.
Risk mitigation plan.
And here's one of the costs.
So the question I was going to ask when we got done with this, if I didn't see it, is, do you have a risk mitigation plan?
For each of these, listed items, we do have basically ideas or ideas set of how we could mitigate it. As far as allocating who might do it. Sometimes we would be able to pinpoint this kind of test.
Just ideas would be
But
good.
at this point, kind of the steps along the way would be what you need.
Right.
Right. And then you get to go to your program manager and say, I don't have enough money. The problem is, if you're worried about this risk, give me the money to solve the problem.
I have a sneaking suspicion that our risk list will be getting pretty big here after today. So.
I think I heard you say that the insertion accuracy was something you were worried about, but you pretty much dismissed that concern. Did I hear you say that?
I said that as far as insertion accuracy, we addressed it by performing analysis on the orbits team, doing sensitivity analysis for orbits and ABC to ensure that our spacecraft will be aligned properly to within some percentage or some degree to ensure the probe is dropped correctly within its window.
Or if we had to
I thought I got a different answer this morning.
Yeah.
Whatever.
Any more questions, just risk related? We're about to step into reliability. And with that said, here we go. This is the breakdown of our reliability requirements. As mentioned earlier in the class, we had two fundamental requirements. Our first got the RFP, the requirement was 80% mission reliability for the whole mission. After doing some first order analysis, we realized that we weren't getting anywhere close to that number. So working with the customer and showing them our analysis, he was able to lean on it and turn it into what it is now, which is the orbiter and the probe must have an 80% probability of success, and the two UPS vehicles, each with their probes, will have a total mission success with the orbiter of 40. So basically, you have 6 space vehicles there. All of them need to combine to have a 40% probability of success. Also, we defined mission success, the 40%, as the mission reliability, or the probability of success for all 6 vehicles to successfully accomplish the mission. Any questions on how we define that? All right. Shaka, please.
Actually, I have one question. So, going back, so that 0.4% probability?
Yeah.
So then what is your probability of the UPS? 40.
There is no...
It's 40 for the whole
40 for the whole thing. There is no... I mean, it has to obviously be above 40, but the actual specific numbers for the UPS vehicles is... it's not specifically stated. However, the combination of them, along with the orbiter, must be...
So 0.4 divided by 0.8 is the probability for both UPS vehicles. You took the square root and you have the allocation.
We basically said.
You do that in your head?
Helps out.
25.
So I guess moving forward, next slide, please. So the analysis methods we employed for reliability calculations was a part count analysis, which is a good first order approach to calculating reliability. It generally yields conservative results, and it requires less detailed information on the component level. As an undergraduate class, we simply didn't have the resources or the detailed information required to do other more complex or sophisticated approaches such as part stress analysis. So with that, we were able to obtain the required information necessary to perform part count analysis, which would be the time of operation of the parts, mission duration, there's redundancy mode, and the failure rates, which we would obtain failure rates either from industry professionals, some of which are in the audience right now, and our customer. We would also develop reliability block diagrams using the subsystem's functional block diagrams. We'll go into that on the next slide, but also we would use those to determine any single point failures that may be present within the subsystem. Whenever applicable, we apply duty cycles. This was analysis that was particularly prevalent in the propulsions and comm subsystems, but they were applied in other places as well. And finally, to help improve our reliability, or at least improve the answers were to improve our reliability, we would employ a thermal adjustment strategy, which we'll also talk about soon. Next slide, please. So this is an example of a reliability block diagram. We derived it again from a functional block diagram. I'm sorry if the print is too small, but you should be able to get the takeaway message from it. This is from the attitude determination and control system for the orbiter. You can easily identify, that the items are cross-strap redundant. They're, the star trackers, for instance, are redundant, 3 for 2, and we basically use these to go through a subsystem, identify where the critical items are, and take necessary measures to mitigate any potential single-point failures or improve reliability. Also, it's important to note that we modeled these down to the component level, not the nuts and bolts level, which we hope to obtain. But again, simply because we didn't have the information, we had to stop at the component level. Next slide, please. The thermal adjustment strategy was employed to help get better, more accurate numbers for our, for our reliability calculations. It was obtained from a reliability engineering handbook, which stated for first order calculations of reliability, for every 10-degree decrease in operating temperature of a component, you can realize a 1.25 factor increase in effective MTBF. We can see this on this plot over here with an example of a star tracker that over a baseline of 21 years of a star tracker, we assume that the baseline temperature, operating temperature of about 20 degrees, that it has about 84% reliability over 21 years. However, if we apply the thermal adjustment strategy, we can see as we lower the operating temperature, the reliability could potentially be increased to up above 90%. We applied this to the ADCS system as well as some others and saw, for instance, using this method, we were able to increase ADCS from about 88% reliability to above 95%. It's also very important to stress here that we would never use this strategy to drop a component below its specified operating temperature. So we always kept it within its operational limits. If there are no questions, we'll move on to the next slide.
Well, I should ask everybody here, that only does apply to electronic devices, right?
Yeah, it was only applied to electronic devices.
Yeah.
We wouldn't
not primarily, only.
Yeah. Yeah, so.
Yeah, it doesn't work with clusters.
Yeah, we didn't apply it to those. So, moment you all been waiting for, this is our reliability mission breakdown. All the components in black boxes indicate either an allocated reliability, simply because we didn't have the information necessary to calculate it, or it implies a subsystem which is not present on the vehicle. For instance, there is no prop system or ADC on the probe. Listed down at the bottom, we see the 2 mission requirements, reliability of the orbiter and probe, and the total mission reliability. I apologize, Dr. A. I'm sure you noticed the sig figs.
No, this is fine here. We were actually talking about this during the break.
Oh, yeah?
Typically you see five places.
Okay. Well, it's just, if you notice the main mission reliability numbers have more sig figs than the numbers.
So everybody does it that way, and everybody recognizes that it doesn't matter how many digits you put out, they're all wrong. But they're great for comparison and great for relative evaluation. So everybody, that's kind of been accepted in the industry. Since you can't really measure this anyway. The other stuff that we were getting on you about, somebody can actually go and measure that, but not to the significant digits you guys put down. Does that make sense? It does.
So is this now, is your requirement in the RFP to compute a number for mission reliability, probability of mission success?
Well, we had a requirement of meeting a certain mission success. I mean, it's up to us to decide how we go about calculating it. We went with a part count analysis.
Well, all what I can say is, and I'm an old guy, sure, but my data ends 10 years ago, that for the 40 years I was at JPL, we were very careful never to quote probability of mission success, because it's a quick way to get canceled. You're never going to get a number that's going to be very satisfying.
Because if the number's 1, nobody believes you, and if the number is anything lower than that, then they think you're not doing a good job and you fail.
No, but it's 1 or 0, really. Don't volunteer it. never volunteer this. Unless if you're asked to produce it, then you gotta do something.
So perhaps in future presentation, I should say, yes, we met them.
We're good. We're good.
So you made your 40%, but on the Orbiter and Pro, is that, did you make it? You were looking for 80%?
We were looking for 80%. Our last set of Jamin.
Is there any particular reason why the Pro Orbiter comms is a little lower than the other ones? Because you have the same speed strategy on all of them.
Yes, the difference between those numbers, all the different probes and all the vehicles in general, is we apply different time constraints to them. Therefore, the orbiter on the probe on the orbiter is obviously off. Its mission lifetime is a little bit,
and then you push the model over. We're good.
So does your mission reliability include the launch vehicle?
No, the customer, our analysis is not including the reliability launch vehicle, just our system as it exists. Obviously, if we included
How about the payload launch adapter?
no, we did not include the payload attached fitting either into our analysis, mainly because we weren't sure. I mean, we assume it to be a structure.
The launch vehicle?
Essentially, yeah. We didn't count that as a launch vehicle.
So really, you're
Yeah, and that's.
got
Oh yeah, the Pyros again. That's a rounding error. I guess we'll keep this plot on the next slide. We'll see that from these plots we can identify sources of what's bringing our reliability down, and obviously, you guys can guess the long mission life is a big factor. Between 15 and 21 years between the UPS vehicles or the orbiters. So, and obviously the way we've addressed that is anywhere possible we try to make our systems as redundant and robust as possible. Sometimes make components triply redundant. We have 5 reaction wheels where we can. So,
are you saying in this first build that really every box has a design requirement?
yes.
In terms of performance, parameters sort of drifted back. You guys were going at 16.5 years. So you're saying that your program is accounting for the fact that you're going to get the lifetime design life of the box at 16.5 years.
I mean, we're basically saying
that's done via worst case analysis, electronic box, or life test at the same mechanism.
Yeah,
I would make sure that that's called for. There could be something that goes with the risk list to make sure that it's actually done.
and that's how we have to think about moving forward with this, because of the mere fact that we have to just face the facts that many of our components are not rated to last more than 15 years. So a lot of the spec sheets will just maybe say like 15 and more, but we're definitely in the and more section. For instance.
So that bullet really is not necessarily true.
We just I want to make sure you guys knew that we're not just assuming components will just work forever, as long as we follow these.
If you look down the first column there, would you use those numbers to rebalance the risk across the system and the investment to try to make things to look like that solid? I mean, you have something up there that's 997, and you have something else that's 891. That would suggest that less more in the 891 and take some away from the 997. If you really believe it.
So like you were saying, we're trying to allocate the
Well, I think that the more useful thing, rather than quoting bottom line probability of success, is to use the information to try to see where you can invest more and where you can invest less in terms of.
And propulsion at 991 seems pretty low. Propulsion systems
It actually was.
are usually pretty high for reliability.
It was a bit higher. That we took a drop last week when we calculated the reliability of all the welds that we would require on the system. That may have been an overestimate on the hit we would take.
So it was pressure in the test system.
Usually that's like that.
So you heard
Mars observer.
Yeah. I can't take it. I can't.
I guess also with the other sources
in
of
general,
sources of reliability drop. Obviously, the ASRGs are a big concern, and that's why we've had to work so hard with the orbiter to make them 2 out of 3 redundant. However, with the UPS vehicles, we just had to take the hit on reliability. Also, as you can imagine, the number of space vehicles factors in. We have 6 space vehicles, 3 probes, 2 UPS, and an orbiter that need to work in series in order to complete all the science mission requirements. So, I mean, again, that's one reason why the customer was willing to drop the overall mission success requirement.
But you get 90% of it with far fewer than
yeah, it's like I said, it's definitely something, when we present this to the customer, you can look at it and say, well, if we're getting 90% from this one vehicle, then maybe invest more in that. Again, that's for him to decide. If there's no more questions.
So you have block diagrams for, I know you only show one, but you have reliability block diagrams for all the subsystems?
We developed them for all the subsystems except for kind of those borderline systems that we're talking about, harnessing and pyros. I mean, I guess harnessing can kind of be realized through connections between subsystems. But, yeah, for all the primary, the big 5 or 6, we have developed block diagrams for it. And that's primarily how we conduct our analysis.
Yeah, it's pretty true. I look at the back of the propulsion.
Yeah, it was up around 95% prior to the weld calculations. So, yeah. All right.
But did you take into account that you had, didn't you say earlier that right before a leak you have the 2 lag valves that count for that kind of thing. But for a leak in the line, you had I guess you had a pyro or something in front of each of the fuel line of each thruster.
Yes.
Did you take that into account? Because if you had a leak in any of those wells, that was mitigated.
Actually, no, we did not take that analysis.
That's probably going to be too conservative.
Yeah, I'm sure if we, obviously, if we.
Take it.
All right. All right, thank you very much. I will now introduce INT, which will be spoken for by Jerry. Any shots?